All right, what's up, guys? Welcome back. We've got the key for the review for assessment 4 here. So first one is just knowing these equations. So I put them in there. That should be something you have handy when you take the assessment. So you're ready to answer problems related to those. And we'll get a couple other ones that you might use, but all stem from this as we go through this. So example of an object with a lot of momentum, an object with very little. A car going 75 miles per hour on the highway is a lot. And how about a um, dog walking down the sidewalk is a little. Some kids gave me an object not moving, which I would argue that an object not moving has no momentum, so that's not very little. It's none at all, so that's a difference there. So I made that comment on some of your assignments if you turned it in already. Now here, moving object collides with a stationary object, they stay together. So that's an inelastic collision. I don't need you to know that term, but what will always happen to the speed of the moving object? So this one is moving, hits this one, and they move together. So always, in this situation, the speed will decrease because more mass is moving. And so because momentum is conserved and is now more mass moving together, the speed is going to go down. And so here, momentum is always conserved. I spelled that wrong. Conserved in a collision, meaning the total amount of before the collision is equal to the total amount after the collision. So let's bold those so you know what the answer was. Now here, some kids that look like maybe they guessed on this or didn't do the math related to it. So you got to look at this as a before and after. And that's really, I don't know any other way that you would solve this one. So before I got the 3 kilogram object moving rightward at 2 meters per second. So that's 6 units of momentum. And the other object is 4 kilograms moving at 1 meter per second rightward. So that's 4 units of momentum, so 10 kilogram meter per second is our total momentum before the collision, which means that that has to be what the momentum, excuse me, after the collision is. So afterwards, this object is moving rightward at 1.5, so 4 times 1.5 is 6. So 6 plus the momentum of the other object, so we'll say mass times velocity of the other one, and that's got to equal 10. So here's what we need to be able to think through, is that that mass times velocity has got to equal 4. Sorry about that, capital. And we know the mass of that other object is 3 kilograms. So I'm going to just plug 3 into that. So 3 times velocity equals 4. And do some algebra, and that means velocity is going to equal 4 divided by 3, or 1.33 meters per second. So that's how you would solve that one. Now here, this is like our one of the simulations we did with the exploding carts. So if cart A, 10 kilograms, moves 3 meters per second, how fast does cart B, which is twice as massive? So if it's twice as massive, it moves half the speed. So that's 1.5 meters per second. How much momentum before the collision? So there's those two carts are sitting there, not moving. So they have 0 momentum before the collision. And if they have 0 before, then that means that they have 0 after. So a lot of kids were doing some math here for these, and you don't need to do that. So that's a purely conceptual question. How much kinetic energy does cart A have after the explosion? So what you've got to remember I'm going to put a space in here. So What you've got to use for this next set of questions is kinetic energy equals 1/2 mv squared. So how much does A have after the explosion? So mass 10, velocity 3. So half of 10, which is 5, times 3 squared, or 9. So 5 times 9 gets me 45 joules. Cart B, 20 kilograms, 1.5 meters per second. So half of 20, which is 10, times 1.5 squared, which is 15 times 1.5 is 22.5 joules. And if they have that much energy each after the explosion, then we know that there was that much potential energy before that was stored in the plunger that shot them apart. So that makes that 45 plus 22.5, which is 67.5 joules. And make sure you're using the correct unit on these. So here, this work one, you've got to lift the box up. So you are lifting this box 100 newtons, so force times distance. So you're just doing, here you don't have to multiply by 10 because it's already the weight of this. So 100 times 1.5 is 150 joules of work. And you carry it over to the shelf. Now here, this is something we talked about in class, but because the work, the force has to be in the same direction as the distance. And here I'm carrying it, so I'm putting an upward force on it, but moving it horizontally. So no work is done in that situation because the force and displacement, or force and distance, are perpendicular to each other. They're not in the same direction. And then here, power is work, 150, divided by time, which was 3 seconds. So I would do 150 divided by 3, which gives me 50 watts. Watt. Example of you using a lot of power and a little bit of power while doing the same amount of work. Some of you use your stair examples, which is fine. I would encourage you to, hopefully you can think of other examples like that. But maybe you lifting a, what might be something you lift at home? We'll say a box. Lift a box quickly versus slowly. So this says you'd use a lot of power to lift it quickly versus a little bit to do it slowly. Here's a pendulum, classic energy conversion example. At position A, it's all potential energy. At position B, it's swung down here. This is all kinetic energy. And then at position C, half KE and half PE. Now, 10 joules of work to wind up the 2 kilogram toy, travels 3 meters per second. So work should equal the kinetic energy. So should be 10 joules theoretically. But the kinetic energy equals 1/2 mv squared. And so we'll calculate that. Half of mass, so 1 times v squared, which is 3 squared. So it actually has 9 joules. So it should be 10, and it is 9. So 1 joule was lost as heat, most likely due to friction on the inside of that toy. Someone uses a Hot Wheels track as a ramp, raises the car to a height of 0.3 meters. So potential energy equals mgh, so mass times 10 times height. So 0.5 times 10, which is 5, times 0.3. So 5 times 0.3 is 1.5 joules. How fast should it be traveling at the bottom? So we just went over this again today in class. So PE at the top should equal kinetic energy at the bottom. So I think the easiest way to do this is mgh equals 1/2 mv squared. I'm getting so sick of typing that. And then like we talked about in class, we can take out the mass here because it's on both sides. So that gives me, whoops, that gives me GH. So it's at a height of 0.3 times 10. So we'll say 3 equals 1/2 v squared. And so to get rid of that half, I'd multiply both sides by 2, or you divide both sides by half. So 6 equals v squared. And then I take the square root, and the square root of 6, I know it from earlier. What is it? 2.4 or something like that. 2.45. So 2.45 meters per second equals the velocity. So you just got to know to use that formula there. And once you know that, then that becomes hopefully straightforward. I'm ranking from highest potential to lowest, so I just use height. So it's going to go 1, 2, 4, 3. 1 is greater than 2 is greater than 4 is greater than 3. How much potential energy does it have at position 1? So m times g times h, so 50 times 10, 500 times 4 equals 2,000 joules. How much kinetic energy does it have at position 3? So here it's on the ground, so it's all the potential is converted to kinetic, so that's going to be 2,000. How much potential energy at position 2? So m, 50, times g times 10, 500, times a height of 3, 500 times 3 is 1,500. So if it started with 2,000 joules of energy and at position 2 it has 1,500 of potential, then that must mean it has 500 joules of kinetic energy. Here I have the 1 kilogram arrow and a bow. I pull back 4 meters, force of 100 newtons. Work is force times distance, so 100 times 4. So 100 times 4 equals 400 joules. If I do that much work, then it has that much potential energy. So those are the same. So I don't have to do any MGH here, would give me a really wrong answer. So if I did this much work, it has this much potential energy. I let it go, and then it has 400 joules of kinetic energy. And then I want to know how fast it's going to be going. So now I know 400 equals 1/2 mv squared. So I got to do some algebra again. And the mass here is 1 kilogram. So we'll say half of 1. We'll just change that to 0.5. So then I divide both sides by 0.5. I get 800 equals v squared. And I've got to take the square root of 800, which the square root of 800 is 800 square root is 28.28. So 28, we'll say 28.3 meters per second. Here, total amount of energy is always conserved. Explain what this means is that the energy changes forms, but isn't gained, well, we shouldn't say gained, isn't created or destroyed. Almost done here. Something that converts kinetic energy into electrical. So that could be like a generator is what most kids are saying, or they're saying windmills, something like that. That's fine. Potential energy into sound. So your cell phone runs on a battery. So if it rings, I would say your cell phone is a great example, or dings or something. And your food is an example of chemical potential energy that you use to do things throughout the day. So there you have it. Use the beginning of class time before the assessment to ask any questions, and we'll see you later.